Hello people! This little board that I'm holding here is the front panel control out of an old Lexmark T630 laser printer. And this is a printer that I had taken apart like a very long time ago. And I still have this kicking around. When I took it out of the printer, I thought it was actually kind of interesting. And I have a hunch that this display here is a HD44780 compatible display. And if I could figure out the pinout for it, I could make use of it. And I've actually thought of a project that this would actually be perfect for, due to the fact that it's very thin and compact, and that the entirety of the electronics are pretty much on the glass here. So it's got the controller chip in there. There is another IC on this board here, although this is basically just to interface the printer to the LCD, and also for these buttons that are up in the front. Now, if you're not familiar with the term HD44780, that's a Hitachi chip that was designed for the use in a bunch of these like character displays. And it's pretty much what all of these are like based off of. And there may be a few like exotic ones here and there, but for the most part, any small like character LCD that you might come across, it's more likely than not going to be some sort of HD 44780 compatible chip on it. And like I've got a few examples here. For the most part, a lot of times nowadays, you're going to find these that have like the chip on board. And so like the chip itself is not specifically numbered. I do have one here that has an actual HD44780 chip on it, along with the accompanying like support chips for all the segments that it's going to be controlling on the panel. And I've got this one here that does not have an HD44780 specific chip. It does have an SED1278F. But if you look up the datasheet for a 44780 and this chip right here, they're practically identical. For example, taking a look here at the pinout for this SED1278F, you can see how we have like the DB1 here, DB0E, and pretty much all the control stuff is like on this side of the chip. And we've also got some data lines like up here, and then a bunch of segments and common pins like all around the chip. If we take a look at the pinout for the actual HD44780, we can see that it's basically the exact same thing. We've got our data pins up here, along with the common and segments, and also like a bunch of control lines over on this same side. The only time you might find like an actual difference could be like in the character fonts. Some might include like some extra characters that others don't, or they might have like some other symbols and shapes that others don't. In the case of like these two, the character font ROMs are, I mean, they're identical. Like if you see here that we've got a 0, we've got like the @ symbol, a P, this little slash or apostrophe or whatever, and then this little P. If we take a look at the one for the HD44780, and this is a ROM code A00, which is exactly what's on this board here, we can see that it's like the exact same thing. So basically the main difference is just going to be in how many characters you have across and how many lines. So for example here, this is like a 4-line 40 character display. And this is like a 2x16 because it's got like a bigger characters. And then this one here is like a 2x40. Now, as I was saying, so I like the fact that this one's really compact and thin. As you can see, this single line 16 character display is quite a bit bigger compared to the just glass only one. And so for my purposes, I like the fact that this is not going to take up very much space. And although it doesn't have a backlight or anything like that, I could probably easily add one. I've got this thing here that came out of, I think this came out of an amplifier. It was just to like light up the branding on it. And it has like 2 LEDs on the side here, but I could actually just kind of like cut out a chunk of that. And I think these LEDs are burnt out actually. They don't light up, but it'd be easy to replace it. And then I could actually stick that like underneath there and have a backlight 2x16 character display. And even with that, it still takes up a lot less space than something like this would. Unfortunately, there's no number on this display that I can like look up so I can like try to find a data sheet for it or something. There is some stuff printed down here on the bottom. It says G517F/10C, but I've tried looking that up. Nothing comes up. And there's also like nothing printed in the back that I can look up or anything. But what makes me say that I suspect that this is a 44780 compatible display? Well, first of all, the fact that it's got 14 pins. Most of these character displays that you might come across, they all use at least 14 pins for the communication section. And then they have an extra 2 that are sometimes used for the backlight. As you can see, this one here does not have a backlight. The second clue we have is that the pins that are used to control the LCD are wired in a way that pretty much closely resembles what you would use if you wanted to control one of these panels in 4-bit mode. That means that not all of the pins are used, and you can, I don't know if you can see here, but like these 4 pins are not used. These 4 down here are used, and then the ones over on this side are used. So when you use one of these displays in 4-bit mode, you only use 4 of the pins, and that's usually going to be like D7 through D4, which leads me to believe that this outer pin here is D7, and the inner one right here is going to be D4, so that means that this would be D3 to D0, and those are not used. Now, I say that this closely resembles the standard pinout on an HD44780 compatible display, because the pins that are used on this side don't exactly match up with what you'd find for the pinout on like another standard sort of wired display like this one. But the good thing is that this display being mounted to this board means that some of the work's already been done for us. And so it's easy to figure out what ground is, what VCC is, and what the contrast control pin is. That means we only have to figure out which ones the control lines are, which, I mean, it's going to be these 3. I just don't know which one's like what. And also if the data going to it is actual, HD44780 ROM compatible data. But we can easily figure that out. And that's the whole reason why I thought I'd make this video, because I can show you like the process I'm going to go through to figure out, what exactly this is getting. Now, one thing that's actually going to make this super easy to figure out is the fact that this chip here feeds data to this display without being connected to a printer. I found that out by applying 5 volts to the ground and the VDD pin, and saw that it immediately filled the screen with these little diamond shapes on like every segment. So what we're going to do is we're actually going to, I'm going to solder in this little connector here to the ground and the 5 volt line coming in. And then on the opposite side, I'm going to use the 3 data or the 4 data lines, the 3 control lines, and the 5 volt line. And I'm going to hook those up to one of these boards with the Cypress chip on it. And then we can use Pulse View to capture the data that this chip sends to the display and analyze it to see if it kind of matches what an HD44780 chip would be expecting to receive as far as like commands and data go. And of course, we're not going to get like an entire command set or anything like that, but we can use this as kind of like the starting block to see how close, it actually is to a standard like HD44780. And once we've got that figured out, then there's like a few other things we can do to figure out maybe the entire like character set that's present on it, and also the complete pinout. Now, as I kind of mentioned a little bit ago, that the pinout on this display doesn't exactly match up what we'd expect to find on like a standard little character display. And I say that because on this display, pin 1 is ground, pin 2 is the contrast control, 3, 4, and 5 are going to be the control lines, and pin 6 is VDD, which is the one that goes to 5 volts. On a standard display, pin 1 would be VSS, which is ground, pin 2 would be VDD, and on here it's not, and pin 3 would be VEE, which is the contrast control. So the 3 pins that we need to still figure out is RS, RW, and the enable pin. And that's going to be these 3, but like I said, I don't know which one's which at the moment. And I'm fairly confident that pin 11 through 14 are going to be D7 through D4. Boy, trying to write on this little post-it while I'm just looking at the screen is kind of weird. On the board here, our VEE pin, which is the contrast control pin, goes to a 330K resistor to ground, and it also connects to an 8.4K resistor to VDD, which is 5 volts coming in. And I don't know if the printer actually had like settings to control the contrast on the display. So it's possible that at some point this pin also goes to the chip that's on here. I actually didn't check that, but it's not too important because like I said, we can see stuff on the display. So as long as we can see stuff on the display, that's pretty much all we need to know. I also did write the 2 pins, the ground and the VDD, that are on that 5-pin connector. The other pins are going to be probably like data in, maybe a clock, and data out, maybe. I don't know. Although that's not really important for our purposes here. Okay, so I've got the power line soldered to the connector coming in. And as I apply power, you'll see that the screen will come alive and displays all the characters with that little diamond shape. Now, that little diamond shape does not show up on the Hitachi datasheet for the 44780. So either it's a character that's stored in its ROM, or it's a character that's being stored to RAM and then displayed on the segments. If it's a custom character, then that's going to be very useful because that means that it's accessing RAM, and so we'll know where that RAM address is located at. And it could be the same as the HD44780 RAM, or it could be something totally different, but we'll find out that way. Okay, I've got everything wired and ready to do a logic capture. So the way I wired it here is I did the data pins go to port B, pins 7 through 4 over here on this side. And port B is the port that this chip uses to capture like the first 8 bits. We can do a total of 16 bits of capture, but we only really need 8 for this. And then the other 4 inputs that we're going to use are wired to the 5-volt line, which I'm going to use to trigger the capture. And then the other 3 unknown lines that we're going to try to figure out. And then obviously we need a ground, because without that, we're not going to get a reliable capture. So I'm going to switch over now to pulse view. And one thing I didn't notice about pulse view until I did the video on the multimeter OLED screen replacement is how small everything shows up on the bottom. So I'll try to blow it up in post after I capture all this so that we can see, you know, like what sort of commands and stuff are like showing up on the bottom. But we need to do a little bit of setup here. So I'm going to increase the sample size to, I don't know, let's say 20 million samples. And I can turn this up as high as, it kind of craps out at some point, but I think 12 megahertz should be more than enough for this. Now the other thing is here, we can get rid of D15 through D8 because we don't need those. We're not going to be monitoring those. We can do that from up here. All right, so now we just have those. All right, so we're left with D0 through D7. And as I said, D7 and all the way up to D4, that's going to be the 4 bits. So I'm just going to leave those as is. And then D3, D2, and D1, those are our unknowns. So I'm just going to name those here unknown 1, unknown 2, and unknown 3. The D0, which is the one that I'm going to use to trigger, I'm just going to name that trig. And I'm going to set it so that it captures on the rising edge, because obviously the voltage is going to be going high. So we're going to do that. And now we've got that all set up. And let's go ahead and start a capture. I'm going to hit the run button, and then as soon as I apply power to the display, we should see it populate here on the screen. So here we go. I'm going to click run. And so you can see nothing happens just yet. I'm working on connecting power to the display, and it should trigger now. Okay, I'm going to... there we go. So we caught something. Okay, so if we zoom in here into the beginning of the capture, this is where the trigger goes high, and we can see that everything else goes high as well. One of our unknown lines goes low, and we also get a change on a couple of the data lines here. But none of these other ones are changing as data is changing on the 4 data pins. So I don't know what this would be doing here, but it seems to be doing some sort of like repetitive pattern, but that wouldn't be getting written to the screen because none of these are clocking in any sort of way. And that just happens for a bit. Eventually it settles everything down to 0 state here. And then we go a little bit further and we see that these now all go low. So now all 3 of these control lines are low. And I don't think that this is actually having anything to do with controlling the display until we get to this section here. Now we see here that now these 2 are doing some sort of pulsing. We got some data in here going into the display. So this would be all 1s. It appears that maybe this one here is doing the latching. So when it gets to this point, it would latch all 4 of these as an F. Over here, it goes low. All these are 0s. And then they turn back into 1s. And then it does another pulse here, but that's not entirely making sense just yet. This here appears to be clocking in a, what would that be? That would be a 3. But we see that this line here went low. And we see we've got kind of a repetitive pattern going here again. Now I'm wondering if this has a decoder for HD44780. So let's look. Okay, so there's no decoder here for HD44780, but I think what I might be able to do is just use this parallel decoder, and we'll put it right here, except that we're going to have to set which lines are what. Actually, we don't need to because it's already set up for us. So it knows that the D4 through D7 here are the data, and the D0 through D3 are just going to show up as a 0 on the lower nibble of what's decoded because there's nothing set for those. So yeah, this will work. So the 3 pins that we want to figure out is which one is RS, which is the register select pin. It says that if it's a 0, it's an instruction, and if it's 1, it's data. Then we need to figure out which one's the read and write line. This one here is probably going to be set to 0 most of the time because it's just going to be writing to the display. It doesn't really need to read anything back, I don't think. And E, that's when it starts the data read and write. So this one here is going to be the one that's pulsing to either write the instruction or data. And if we scroll down a bit to the section of the datasheet where it says on how to interface to a 4-bit MPU, we get this little diagram here that some of this stuff kind of matches what we've got going on our capture. So we can see here that this E here goes high, goes low for just a little bit, goes high again, and then goes low for an extended period before it does that again. And if we look at what we captured, we've got that going on right here. So it appears that our unknown number 3 is going to be our E. So I'm just going to go ahead and label that E now since we're pretty sure that that's what's going to be. And on my little post-it here, that's pin number 5. So I'm just going to put an E right there. Now, unfortunately, we don't have the exact same replica as this on our capture. So here we see that we've got an instruction being written, and then it's checking the busy flag. So that means that it's reading back data. And then after that, it's doing another write here. On ours, we see that we just got this one here going high for the entirety of this little operation right there. This one here, though, does go low for a little bit. Although I just realized I was looking at a totally different section, but it does appear that this actually is going to match the standard pinout. So it does appear like the other 2 pins, the top is going to be the register select, and then the pin number 4 is going to be the read write. So this does match like the standard pinout. It's only a difference of the ground and the VDD and the VEE pins. Let's see if we can figure out what's going on in this section right here. So we know that when the RS line, which is the register select, is 0, that's going to be an instruction. And when it's 1, that's going to be data. So here we see that we've got 0, which means that it's going to be an instruction. And read and write being 1 means that it's going to be reading data. And when the E goes high, that's when the chip inside the display is going to perform its action. So we're going to write or read an instruction back from the chip, which sends back all zeros, it looks like. And since we're only focused on the higher nibble here, we're going to ignore the low one. So it sends out a 0, and then it stops asserting the E line, and it looks like the pins go high. And then once it does the second clock, it sends out another 0. So it appears here that the chip on the board there is reading a 00 from the display, and then after a while it turns this the read write line into a 0, which means that now it's going to write something, but it's still an instruction, and we can see that the E line here is not doing anything. So now it appears that the microcontroller is the one that's controlling the lines now, and it's making line data 5 high, which means it's going to be a 2. And we move a little bit further, and it writes that 2. And then we keep going a little bit more. And now the little chip on the board there now is writing an 8. And that happens until it gets to this section here where it looks like it's doing another read. So in this section here, it wrote 2-8 to the display. So let's see if we can find out what that's supposed to do from the data sheet. All right, so that appears to match up here with this function set. So we've got 0 and 0 on the RS and the RW lines. And then we saw that we had a value of 2-8 being sent out. So that means that this is 0, this is 0, this is 1, this is 0, this would be 1, and this would be 0. So we see that this instruction is setting the interface data length, the number of display lines, and the character font. And elsewhere in the datasheet, we can find out what that function set actually means, the DL, the N, and the F. So the DL sets the data length, which in our case is 4 bits. So that should be a 0, which in our case it is. N sets the number of display lines, although it doesn't really explain which value means what. So I'm going to assume that if we had a 0 there, it would mean that we have 1 line. But since we have a 1, that means that we have 2 lines. So I think that's what that would mean, because we did have a 1 there. This one here, we had a 0, and it says that that sets the character font. I'm assuming that if that's a 0, it just means that it's using whatever characters are built into the ROM, because I don't think we have another choice. So that seems to make sense. And it also says here that perform the function at the head of the program before executing any instructions. And as we saw on the capture there, that's like the first thing that happens before it goes into any of this other stuff. So now it appears that when it gets to this part, it's doing another read. And let's see what it's reading now. So it reads back an 8, and then it reads back a 0. Although this line here appears to goes low in the middle of it doing its operation. So I don't know if that means that it's 0, 0, or if it's actually 8, 0. But once again, here in the datasheet, we can see that that corresponds to read busy flag and address, because it was a 0 on the RS line and it was a 1 on the read line. So since it said 80 at first, this right here is the busy flag. And if that's 1, then it means that it's busy. So it looks like it was busy for a bit, and then it stopped being busy. And then the rest of the bits are for the address counter contents, apparently. But that was apparently all zeros, because we saw that it sent out 80, but then it changed to basically a 00. So it appears that a lot of sections here are basically just doing a read to see if the display is busy at all, because it checked here, and I'm guessing that it saw that it was still busy. So it just waited a little bit, and then it checked to see if it was busy again. And at this time it says 00. So now it's not busy. So now it looks like it's going to write 0 and then a 6. And that's also still a instruction. So that seems to be doing this entry mode set instruction. And since this one here is always going to be a 1, that means that these two are the ones that it's either setting or not setting. So it's setting this ID as a 1, and it's setting the S as a 0. So let's see what these do. So here it is, entry mode set. So since this is 1, it means that it's going to increment the DRAM address by 1 when a character code is written into or read from DRAM. So that basically just means that when it writes a character, it's automatically going to increment the memory address. And then we saw that S was 0, and that says that it shifts the entire display either to the right, if this equals 0, or to the left when this is 1. But we saw that we had a 0 there, so that means that the display does not shift if S is 0. So we're not going to get any shifting here. So far it all seems like a pretty standard setup. And then once again, it checks to see if the display is busy. And it looks like right here it is still busy. And then right here it's not busy anymore. So then it writes another command. This time it appears to be 0E. And that's going to be display on-off control. It's going to be setting these bits down here. So, and since we had 06, that means that this is going to be a 1, this is going to be a 1, this is going to be a 0 because it's an E. So if we had all 4 of these as 1s, then we'd have an F. And D, it says the entire display on or off. C controls the cursor on and off. And B is the blinking of cursor position character. And so that makes sense. The display is on when D is 1, which it is. The cursor is displayed when C is 1 and not displayed when C is 0. And this doesn't really seem to matter in our case because we fill the entire screen with those little diamond shapes. And since B is 0, it appears that we're not going to get any blinking, which also makes sense. Okay, so we've got 3 instructions out of the way that it's the chip sends to the display. The first one being the function set, the second one being the entry mode, and then the third one being the display control. Check out what the fourth one is. It's 40, which means set the character generator RAM. So sure enough, it appears that it's the actual character information for those little diamond shapes are sent from the chip that's mounted on the board to the display. So the character ROM inside of the display doesn't actually have that little diamond shaped character. So I'm going to go through and I'm just going to like analyze everything, and I'll tell you like what I find and like how it's generating that little diamond shape. And then we'll come back because going through this like nibble by nibble, it takes a very long time. Fast forwarding a bit here, and I've got this entire section completely analyzed, and this is what we have. So this little tiny section right here at the beginning, that's the 3 commands that we already saw, where it sets the function set, it does the entry mode and the display control. And then I said that the fourth command was to set the character generator RAM to address 0. So what it does after that is it fills in all 64 bytes of CG RAM with all ones. So what that would be doing is basically making all of those custom characters just completely filled in, like 5x8 blocks of character, basically. And this section right there, that's this portion right here of the capture. So that's all 64 bytes there being written. And I'll just kind of like zoom in here a little bit. Let's move this out of the way. So yeah, it happens 64 times until it gets to about here. And if I zoom out a little bit again, you can see that right here, it's got another section where it seems to be doing something repetitive. And what it's doing in that section is it's reading back all 64 bytes. And like right there in this little section here, it actually resets the CG RAM to address 0 again. So it can start reading from the beginning. So it's checking the busy flag, and it's also incrementing the address. So it's just going all the way until it does all 64 bytes again. And then after it does that, it writes all 64 bytes again. But this time it fills them in with zeros. So it's like it's clearing them all out. And after they're all cleared, it reads them all back again. Now this little portion right here. So what happens at the beginning of this section is right at this point, it clears the display and it sets the display data RAM, which is what DRAM stands for. And we can see that right here, display data RAM. It sets the address to 0, so that means that it's going to start incrementing from the beginning. And it does a bunch of busy flag reads, and at the same time the address is incrementing. So it stays busy for about 49 reads, and when it gets to the 50th one, it's got a value of 67 hex, which means that it's at address 67 hex in the display data RAM. And then when it finally gets to the 51st read there, we see that the address actually becomes 0. So it appears that for these 49 checks that it does to see if it's busy, it must be doing something internally, and it has not set the address to 0 just yet. And I can zoom into this point right here where it gets to almost the end of it. So we can see that right here, it says E70 or E7. So that means here that it's still busy and that the address has incremented to that point. When it gets to this point, it's 6.7. Because this 6 is lower than 8, that means that it's not busy anymore. So if this number here is actually 8 or above, that's when it's busy, because it's already set the bit that corresponds to the a value of 8. And then we see right here that at this point, it's reset the address to 0. So now the little microcontroller on the board there can now send another command, which is 80, which sets the display data RAM to address 0 again. And then it does another display control command, which sets the display to on. It's no cursor, no blinking. For some reason, it does another 80, which also resets the display data RAM to address 0 again. So it repeats these two commands like twice for some reason. I guess it's bored. I mean, it's not like that little microcontroller has anything else to do. And then finally, when we get to this section right here, that's where the drawing for the little diamond character finally happens. So it starts off by writing a 78 hex, which translates to it writing to set a character generator RAM to address 38 hex. And that seems to correspond to writing data to the last 8 bytes of the character generator RAM, which would be like this block right here. And it has an address of what would be like 07 hex. So because each one of these character blocks has 8 bytes in it, the next thing it does is it writes 8 bytes to that block. Now all these values here is not really going to make too much sense just seeing them as numbers. But if we take a look here at what each one of those values represents, we see that it starts off by writing 00 hex, and then 04, 0E, 1F, 1F, 0E, 04, and 00. If we actually draw that out, we can see that the 00 is basically an entire byte of nothing. 04 puts a 1 in the number 2-bit position. 0E is going to show up as 3 of the dots. And so the 1F is all these, another 1F is all that, 0E again, 04, and another byte of 00. And so since each character is only made up of 5x8 dots, that's only going to be this section right here that's used to actually draw a character to the display. These extra 3 bits above it are not going to be used for anything, but it appears that the character generator RAM can actually also be used as sort of like general purpose RAM. So I take it that probably means that you could just write whatever value you want into this entire block or into like individual bytes and read them back if for some reason you need to have like a little bit extra memory for some reason. But we can see how basically that's what draws that little diamond shape. And also we can see here how each nibble here is represented by each one of these values. So 00 is a 0 in these 4 bits, a 0 in that 4 bits, 04, the first 4 bits are 0, and then the next 4 bits equals 4, because it's got the 1 right there lit up, which is in the 4th value position. And so, yeah, that all makes sense. So now that we've got that character drawn to RAM and saved into that 07 hex slot, the next thing it does is it actually draws it out. So it resets the display data RAM to 0, and it writes 07 hex 16 times to the display data RAM. So every time it does a write, it automatically increments, since we set it to like automatically increment up here. So that's where it writes all 16 of the first line of that diamond shape. So basically that goes up until it reaches an address of 0F hex. After that, it jumps down to set the address to 40 hex, which is the second line of 16 characters. And so once again, it writes that 07 hex 16 times to the display data RAM. That goes all the way until it reaches address 4F, and then that's where it completely stops. And if we take a look right here, we can kind of see that happening. This is where the character generator RAM is written to draw that diamond shape. And this is where it's loaded onto the first 16 characters. And then this is where it's drawn to the bottom 16 characters. And so as soon as it's done doing that, that's where it quits, and it just doesn't do anything anymore. It's done. So yeah, everything that happens here just screams vanilla HD44780 compatible chip, and everything that it does to like draw characters and like set functions and stuff like that on the display is all like 100% compatible. So yeah, this 16:2 character display is just like any other 16:2 character display. It just has the benefit of being very thin because it's basically just the glass, and all the control electronics are just like right there on the glass as well. We just see that the only difference is the pinout for the power and some of the control lines. But other than that, I mean, it's super easy to use. So I'm kind of happy to have this figured out. And this was just kind of a quick and dirty look at the HD44780 chip. And I say quick and dirty because I feel like there's absolutely like no polish to everything I showed here. But I hope that maybe if you were looking for something to kind of explain things a little bit, maybe I at least provided some useful information. But that's going to end up doing it for this one. Thanks you guys for watching, and I'll see you guys around the bench.